We actually have looked at the overview of the processor, the RISC and CISC architecture, and today we will look at the last two, microprocessor system and the comparison between microprocessor and microcontroller. So last week we have looked at this evolution of microprocessor. What are the differences between CISC and RISC? So in short, CISC is the original microprocessor instruction set architecture, and in terms of hardware, it is more complicated, more complex as compared to the RISC. Or we can say that RISC is the software-centric design, where the complexity is more on the software rather than hardware as compared to CISC. So the RISC also, in terms of instruction, we have looked at this already last week. The number of instruction is reduced as compared to CISC, and we have pipeline. We can see in detail what is pipeline. So the purpose of pipeline is to increase the what we call the throughput, the number of instruction that can execute in 1 unit time, right? Is increased in RISC as compared to CISC by using pipeline, and we will see later what is pipeline. Registers are the temporary storage circuit, right? We have learned how to design register in digital design, so it's the same thing, right? It is used to store temporary data before the data or information can be processed by the microprocessor. Load store architecture is introduced to RISC microprocessor, right, where the data in the memory cannot be processed directly using one single instruction. So last week I explained already that to process the data in the memory using RISC microprocessor, you need to bring the data into the CPU, the internal register, and then process the data and then store it back to the memory, right? So it will involve many instructions, right? Instruction to get the data, to load the data, or to read the data from the memory, put in the internal CPU register, and then process the data, save the result in the CPU register, and then store it back to the memory. So for CISC, for RISC microprocessor, you need to have that, right? Meaning that you need to use many instructions in order to process the data in the memory. As compared to the CISC, where you can use a single instruction to process the data in the memory, right? So the example was given last week already, right? So you can refer back to the video last week. And today we will look at the microprocessor system. So to be a complete microprocessor system, you need a CPU. So what is CPU? CPU is central processing unit. comprises of course, the brain, the ALU, arithmetic logic unit, and the internal register, and also the control circuit. All right, that will be the CPU. And all of that component will be in a single IC, all right, in one chip, one IC. Right. So if you look at your computer, for example, if you open the casing of your computer and look at the CPU chip, yeah, so that CPU contain the ALU, the control circuit, and also the internal registers, right? But in order for that microprocessor to be useful, yeah, if we want to use the microprocessor, that microprocessor, we need to connect or interface with the memory. We need to connect to the ROM, we need to connect to the RAM and IO interface, right, in order to use that microprocessor. So if you have this in complete connection like this, we call it microprocessor system. Means that this microprocessor is now can be used to perform computation. All right. So we can write the program, put in the memory. We can read the input from the IO interface, right, and process in the CPU, and we can save in the ROM or RAM, or output back to the IO interface, right? And of course, we have the IO devices. Okay, so that will be the complete microprocessor system. If if we look at our computer today, right? So this will be the basic component for every single computer that we have today, right? We have the CPU, we have the memory, and we have the IO, right? So here is the memory, yeah, just discussed just now. The brain of the microprocessor, right? Memory is to store the data, IO, right? And what is inside the microprocessor? Inside the microprocessor, we have the registers, set of registers, depend on the type of microprocessor that we use. All right. So has some have many registers, some have small number of register, and we have ALU, yeah, to perform arithmetic function, add, subtract, multiply, divide, logic, and or not, and so on. We have program counter. Program counter is another register used as a counter to not to count the program. Actually, this is used to point to the address of the next program or next instruction to be executed. All right, and we have instruction decoder. Okay, so if I can draw the simple microprocessor system and how the microprocessor work, it should be like this. So in general, the microprocessor system has something like this. You will have the ALU, you will have the internal register, Okay, we can have R0, R1, R2 until Rn, right? And we have the bus or connection from each register to the one of the input of the ALU. Right, let's for example, our microprocessor system is 8-bit. And we will have another register called the program counter, or in short, we call it PC. And we have another one circuit, we call it instruction decoder. Instruction decoder, right? And this instruction decoder will send the will connect to the control circuit. So we have the control circuit or controller, right? This is what inside the CPU, and the outside is the memory. So we have the memory, and we have the connection data, right, for input to the memory, and also from memory to the register, right? And the memory has address, right? For example, this is address 0, address 1, address 2, 3, and so on until the last one here. Okay, so this is a simple microprocessor system, and the program will be in the memory, right? And the program is in the form of instruction, all right? And the instruction is in the form of machine code or binary number, right? So, for example, the code for uh, moving data, all right, or get data from memory location 20. So the location 20 is somewhere here. To register R0 is AB, right? And get the data from the location 20 to R1 is AC, right? And so on. So we have the memory in the form of we have the program in the form of machine code. All right. So in every microprocessor, in every computer that we have today, the program is actually in the form of machine code or binary number. Right. We have maybe BC and so on and so forth. Okay. So how the microprocessor work? Okay, so it will when you start your microprocessor, the PC will automatically load it with value 0, such that the microprocessor know where is the first instruction to be executed. All right. So if the PC has 0, program counter, yeah, has 0, so the instruction or the code in location number 0 will be loaded into the instruction decoder AB, right? So the AB will be in the instruction decoder, and the instruction decoder will decode this instruction to generate the control sequence, right? So this control sequence will be based on what is the instruction. So remember this instruction, yeah, we assume that AB is to get the data from memory 20 to uh, location number 20 in the memory to R0, right? So it will generate the control signal. So this control signal is exactly the same as what you have learned in digital design when you design the controller, remember? So this control signal will make the data in location 20. So let's, for example, the data in location 20 is 1, 2. So the microprocessor will get this 1, 2, put in the bus, data bus 1, 2, and bring this to location or to register R0, which is 1, 2 here. And when the microprocessor execute this instruction, yeah, bring or copy or move, we call it move in microprocessor, move the data from this to this, the PC will point, yeah, or increment automatically will point to the next location or the next code to be executed. In our case, which is this one. So the PC will have 1, right? Such that when the microprocessor finish execute this instruction, it will look at the next one, which is this one. So this one, again, it will get the data, get the code and put it in the instruction decoder, AC, all right? We call this process as fetch, all right? When you get the instruction or the code from the memory to the instruction decoder, we call it fetch, right? AC. So AC, we assume that AC is to move the data from 21 to R1. So 21, let's assume that we have 3, 4 here, right? 3, 4. So when the instruction decoder get this, send to the decode the instruction, then the control circuit will generate the code such that the microprocessor can get the value from location 21, which is 3, 4, put on the bus, and then send to R1 here. And at the same time, all right, during the execution of this instruction or this code, the PC will point to the next instruction to be executed, which is number 2, right? Number 2. Such that after finish the second instruction, it will execute instruction number 2. And this process is repeated until we reach the last line of our program in the memory, right? So that is how the computer work actually. So it will work in sequence, all right? From the first instruction, fetch, decode, execute, and then fetch, decode, execute, fetch, decode, execute, right? Get the idea? So this is the general operation of the microprocessor. All the microprocessor that we have today, the working principle is like this, all right? Only the difference is the details, the size, and so on. So we will learn later on how this can be done and how the instruction is executed and so on in detail, all right, in the subsequent chapter. Okay, so that is the function of register. So again, the register is to store the data temporarily here, depend on the instruction that you want to execute. So this example just show you move you copy or get the data from the memory to the register, but haven't processed the data using the ALU, right? So depend if this instruction, for example, is the instruction to add the value of R0 and R1. So again, it will decode and control generate the control signal such that you can add these two and you save back to any register here, right? So that is how the microprocessor work, right? And the register can be 8-bit, 16-bit, 32-bit, 64-bit, depend on the size of the microprocessor that you use. So the original or the first version or first batch of the microprocessor normally is 8-bit. Remember last week, the first microprocessor is Intel 4004. So the size is 4-bit. Yeah, so the register is actually 4-bit. And most of the microprocessor after that is are 8-bit. All right, even the Arduino that you use today is 8-bit, right? And we have a bigger microprocessor, 16-bit. The Intel 8085 is the this one. This one is 16-bit microprocessor. Here is start to be 32-bit already, right? So we have 32-bit microprocessor, and the x86, the older Pentium microprocessor, is 32-bit, and we have for example, today we have iCores 5, i5, i7, i9. So we have 64-bit, right? And also the microprocessor in our uh, mobile phone uh, also 64-bit nowadays, right? And we have the ALU, the ALU. We have the program counter. Just now I explained already what is the function of program counter, which is to point to the next instruction to be executed. All right. So the code, the program to instruct the microprocessor to perform tasks is called instruction. Okay. So the instruction is in the form of machine code or digital value or binary value, right? So in this, I write AB means that this is in hexadecimal AB, yeah. This is in hexadecimal AC and so on, right? And we have instruction decoder. This is instruction decoder to decode the instruction here from the memory, decode such that we can generate the control signal that will control the operation of the microprocessor here, depend on the code or the instruction that we have. So for example, first instruction is to get uh, the data from memory 20. So the control signal will activate the memory location 20 here, such that the data from the location 20 will be on the bus, on the data bus, and also it will enable the load signal of the register R0 to be active, right, in order to store the value from on the bus into R0, right? So that will be the control signal, for example. Okay, so that is the instruction decoder. We will learn in detail this thing in detail when we learn the ARM processor later on, the ARM architecture, right? And we have the buses or the wire that are wires that connect to all the component here. Here I'm not drawing the address bus, yeah, and control bus, control here, right? So we have the address bus. Address bus is the the wire that is used to to access the memory location. All right. So for example, if we want to access location number 0, so the data, the value in on the address bus should be 0. All right. If we want to access location number 1, so the value on the address bus must be 1, and so on. Right. So not shown here, address bus. And we have the data bus. So all of these lines are the data bus. All right, the data bus is the wire that carry the data, right, whether from the memory to the register, or from register to the ALU, and so on, from ALU to the back to register. Here are the data bus. And we have the control bus. Control bus is the signal generated from this, yeah, the wire that carry this control signal, right? Of course, it will go to the register, it will go to the ALU, it will go to the memory, and so on. Now that is the microprocessor concept or microprocessor system, how the microprocessor work. And now what is microcontroller? All right, and Arduino is one of the microcontroller, right? So microcontroller is the integrated chip that contains CPU, RAM, some form of ROM, IO port, and timer, and actually many other peripheral. All right, means that if we look back to this microcontroller, actually is the processor or the IC processor that has everything here, whether it is a CPU, a memory, RAM, ROM, IO interface, all right, in the single IC or single chip, all right. But the microprocessor is actually the processor, only the processor that you have ALU and register and so on, like this. So this is processor. But if you include the memory and all and additional peripheral in one single IC, that will be microcontroller, right? Or this. Yeah, we can draw the microcontroller or explain the microcontroller, the concept of microcontroller like this, where you have on the single IC, you will have the microprocessor inside, you will have RAM inside, you will have the ROM inside, you will have maybe AD converter, analog to digital converter, which is one of the peripheral. You will have a timer, you will have many other things on a single chip. That is microcontroller, right? Or we can explain like this, where CPU, we have only the register, ALU, and control unit. That is microprocessor. All right, but microcontroller, you have the CPU and you have other things, memory in one IC, right? That is microcontroller. So if we look here, it looks like microcontroller is more complicated, right, as compared to the microprocessor, because you have many things inside. And why microcontroller is lower in cost as compared to microprocessor? If you compare the Arduino as compared to the Intel i7 processor, which one is more powerful? Of course, in the Intel i7, more powerful, right? Although you have RAM, ROM, and memory in the Arduino IC, right? Microcontroller IC. That is because uh, although you have everything in one chip for the microcontroller, but the performance, the size, yeah, the size or the computation power is actually less as compared to the microprocessor, right? Because the microcontroller is actually designed for a very specific task to control a particular system, right? This is not intended to perform complicated computing like the microprocessor that we have in our PC. It is used to perform a specific task, normally the control task. So that is why you use the microcontroller, for example, Arduino, to read sensor, some small number of sensors, and then to control, for example, to control simple output, to control the LED, to control the motor, right, or the LCD, just that. All right, but you cannot running complex software. For example, you cannot put the Windows OS on your microcontroller because the memory is very very small actually. All right, because it is designed for a small task, right? And that is why the price, yeah, the cost for the microcontroller is very very cheap. Yeah, you can buy the microcontroller for 10 ringgit, yeah, the small microcontroller, or 20 ringgit, or more powerful microcontroller maybe, but still less than 100 ringgit. All right, so that is the difference between microprocessor and microcontroller. Okay, so if we look at the this table, the comparison in terms of devices, so microcontroller, you have PIC microcontroller, you have Atmel AVR microcontroller, the one in the Arduino Atmel, right? And you have ARM M series microcontroller. Yeah, that is the example of microcontroller. Actually, there are a lot. If you go to the internet, look at the common microcontrollers that we have. We have from Altera also, Nios, but that is not that popular. This is used in on the FPGA, right? We have Freescale, quite popular. Fujitsu, a lot, yeah. Infinite. Intel got microcontroller as well. Yeah, the 8051, 8050, for example, are the popular microcontroller. Microchip, very popular. Last time we at UTHM we use this in the syllabus, right? NXP, the one that we will use uh, in this course, yeah, based on ARM architecture, yeah, from Panasonic, and many more, yeah, a lot, right? So where is Arduino? You cannot see here, right? Because Arduino is actually not we actually we cannot say Arduino is microcontroller. Arduino is actually a board, a circuit that uh, uh, has the microcontroller inside, right? So if you look at this, yeah, Arduino is open source hardware and a software company where the microcontroller inside is actually the Atmel. Where is it? Here, Atmel, right? 8-bit microcontroller. And the latest one got ARM architecture as well. The one with that we use, yeah, ARM Cortex M3, we will use in this course, right? So that is the things. Now let's go back to this. Component, we have the internal for microcontroller. We have internal CPU, we have internal RAM, we have ROM, IO, timers, and a lot more actually inside one IC. But for microprocessor, everything is external. We have external RAM, external ROM, external IO, and so on, right? Application, perform specific function for microcontroller, a small set of signal processing function for digital signal processor, for example. But microprocessor used to perform more tasks that related to general requirement calculation of software, personal computer, and so on and so forth, right? So we run this meeting, the G meeting here, using the microprocessor, right? Because we use this. Yeah, the device here we have Intel x86, x64. Yeah, the iCore 7, iCore 5 now is x64, right? And also the ARM A series processor is the microprocessor as well, right? So we have looked at this already. Now that is the that is the introduction to the concept of microprocessor and microcontroller, right? Now we will go into more detail here by using the ARM processor as our reference. All right, we use ARM processor because it is very popular. All right, or more than 90% processor that we have today is are using ARM architecture, ARM, yeah, ARM architecture. So actually, more than this, a lot more than this. Yeah, we have many things. Even the Qualcomm, very famous. Yeah, in our mobile phone, most of the processor are from this, right? And we have Apple, yeah, the iPhone, the iPad, even iMac, MacBook, yeah, use the ARM architecture. Some uh, MacBook use Intel processor, yeah, but some use the ARM processor, especially the iPad, right? The tablet and the phone, right? Why ARM is very popular in the uh, mobile device? Have you ever wondered that why you very uh, rarely seen the Intel processor in the mobile device? Ya, pernah terfikir tak kenapa the Intel microprocessor, right? Your phone don't use Intel as the mobile or as the processor in your mobile phone. Not really. Intel got Intel got the cheaper version. What the Celeron, the only uh, less than 200 ringgit. Mm. Any other answer? You have Intel M, right? Intel mobile processor. This is a small version of Intel processor as well, but this is not very successful. Even people don't use in the tablet, right? And that is why Windows tablet is not very successful, right? Because Windows is running on the Intel based processor, right? But what is the main reason actually? Any idea? Wireless ah? No. You can have the wireless is just the antenna. This is uh, external peripheral that you can put uh, in your system, right? This is just a processor. This is related to what we have learned just now, not really just now, last week also. Anyone want to try luck kalau betul? Almost there. So yes, the answer is related to power consumption, because remember last week uh, I told you that the power consumption, because the ARM architecture is based on this RISC, right? The Intel microprocessor is CISC, right? Complex instruction set computer. And what is the main uh, difference between these two? The main difference between these two is that the hardware complexity. The CISC is complex in terms of hardware, right? So when you have complex hardware, it your processor will consume more power, right, as compared to the system with less complex hardware, right? So that is the reason actually, right? Because RISC consume less power as compared to CISC. So consume less power means that this is more suitable for mobile device, because mobile device use battery, right? So if your system consume a lot of power, right, your system will drain the battery very fast, right? So that's why it is not suitable for this, right? So you can see, yeah, although the ultrabook that we have, the laptop is quite a, it's a mobile device also, right? But it's still, right, big, bigger as compared to tablet, as compared to mobile phone, and you need to have a bigger battery, right? The size of the battery is a lot more bigger as compared to the tablet that you have. Okay, so that is the main reason actually. Okay, so that is why ARM is everywhere now, because nowadays the mobile device is very important, right? We have at least one with us most of the time, right? So that is why it is more than 90% in the market. So the ARM is does not manufacture silicon, means that ARM not manufacture the microprocessor, means that not make the microprocessor, but design the microprocessor. All right, so just like we design in our digital design, we have the design, right? But we not fabricate the microprocessor on the chip, on the IC, on the silicon, right? So ARM design the microprocessor and sell that design to its partner. We can call it partner. So for example, if Qualcomm want to use the microprocessor, so it will they will purchase the we call it IP, or the microprocessor core, and fabricate their own their own microprocessor. And the name, if you look at, for example, right, if we look at the Qualcomm processor, it will not show the ARM trademark, right? So let's look at this. Yeah. So if you, for example, you open your mobile phone, you will see this Qualcomm Snapdragon, right? There's nothing, uh, there's no sign of ARM microprocessor, right? Because Qualcomm manufacture this chip, and they purchase the the IP already, and the design is inside here, right? They purchase the design and make their own silicon or IC, all right? Same as other microprocessor manufacturer, right? For example, Atmel and XP, Freescale, Apple, all right? All of this, yeah, purchase the ARM core from ARM and then make their own microprocessor, right? So that is why if you search the microprocessor with logo ARM, you will not find any of it, right? So it was founded in 1990, right? The company, the Advanced Reach Machine, right? Actually, the history is was before this, yeah, 1980 something, right? Designed in Cambridge, UK, but the company was founded, yeah, in 1990, right? So the design center is in Cambridge, right, and also in US. That, but the first place is Cambridge, right, and other part as well. And now we have ARM, yeah, has office all around the world, right? And ARM is from advanced RISC machine, so ARISC machine, ARIM. Yeah. Okay, so if we look at the offices, the nearest to us is here, Singapore. Singapore. We don't have in Malaysia, right? Asia Pacific, we have Japan, Taiwan, Korea, China, India, uh, South Asia, and other places. All right, partner, a lot, not enough to put in the slide. Yeah, there are a lot. Yeah, more thousand of IC or microprocessor manufacturers. Right now, let's look at the variant of the ARM microprocessor. Right, so they call it profile. They have three profile. The first one we call it the application profile, or in short, Cortex A. And we have the real-time profile. We call it Cortex R. And we have the microcontroller profile. We call it Cortex M. All right. So the ARM microprocessor has the microprocessor uh, uh, microprocessor part, and also the microcontroller part. All right. So the one that is used in our mobile phone is from the application profile, or A, Cortex A. All right. So it has memory management support, MMU, uh, high performance with low power, right? Can use multitasking, can install OS. So we have the Android, we have Linux inside, right? Not inside. We can install Linux on the uh, for this microprocessor, right? So for example, Cortex A5, A9, A7, all right. We have the real-time profile of Cortex R, right? This is the embedded part. Yeah, it's actually some sort of microcontroller also, but this is the advanced microcontroller where uh, it can be used for the real-time application, where you need this microprocessor for very fast application because of the low latency. All right, for example, the braking system, the automobile braking system, you need the microprocessor that is the microcontroller that is very fast. For example, uh, the automated car, right? When it detects something, so it will act as fast as possible, right? So this one can be used, yeah, the real-time profile. And we have the microcontroller profile, that is the Cortex M, the lowest cost and the lower performance as compared to the first two profile, but it is very useful for the control application, and it is actually a lot more powerful than any other microcontroller that we have in the market, right? Because it is 32-bit as compared to most of the microcontroller that we have in the market is 8-bit, right? This is 32-bit microcontroller, and the cost is actually a little bit more expensive as compared to Arduino, for example, right? The microcontroller, the Cortex M profile. So in this course, we will use the Cortex M profile as the reference, right? So this is Cortex A, the processor. So we have until 2020, 2020, 2021 also got already actually. This is the 64-bit. You also have 32-bit version. R series, not a lot. All right, you have 32, 64-bit also, 32-bit. And for the M series, all devices that we have are the 32-bit, right? And when we look at the performance comparison between uh, the three profiles, so we have the embedded profile, we have the classic, we have the application. Classic is the original ARM, right? Not shown here, right? Not in these three. These three is the modern ARM microprocessor. The classic one is the first version of ARM microprocessor, right? So this is classic. Embedded is profile, art profile, and the M profile, right? So we have the art profile, M profile. So if we look at the capability and performance functionality, you can see that when you want the performance, right, the very best performance and also the capability, you need to go for the application profile, right? And we can see that the microcontroller profile is the in terms of performance is the lowest one, because yes, because microcontroller is small, yeah, it's smaller as compared to the microprocessor. So this one is microprocessor, this one is microcontroller, right? Right, but it is very important, yeah. If we look at uh, the market, right, this one, the embedded one, is actually more than this one, right? Because this one actually everywhere embedded. Yeah, we don't see this because in the electronic devices, for example, the TV, the remote control, the washing machine, right? But the new TV, the smart TV, using the application processor already, because you have the OS inside, right? But still, the embedded one, yeah, in the automobile, yeah, in the car. Nowadays car got a lot of controller, right? A lot of microcontroller inside, electronic inside, right? Using the embedded profile, right? So it is very important. All right, so that will be chapter 1. So before we finish chapter 1, let's do some revision maybe. Yeah, we call it revision. So let's look at this. Explain the differences between the RISC and CISC microprocessor. So I think you can do it, right? So the answer is in the notes. And remember, you need to be able to explain this. Yeah. Number 2, ARM processor has how many profiles? How many? This one you can answer very fast. Just now, we just learned this just now. How many profile we have? 1, 2, 3. Yes, we have 3 profiles. Explain the differences between microprocessor and microcontroller. You should know. Yeah, want to discuss this. Number 4, using the smallest data size possible, either a byte, a half word. Okay, this is maybe new to you. So in order to learn microprocessor, we need to learn. We need to know how we describe the size of, or how we call the size of the data, right? So normally we familiar with byte. So byte is 8-bit, right? But what about 16-bit? 16-bit is called half word, yeah, half word. And 32-bit is word, and 64-bit is actually long word, right? So in microprocessor later on, yeah, we will not, for example, if I want to refer to 16-bit, I will say half word. If I want to refer to 32-bit, I will say word, right? But byte, uh, half word, word, long word, for example, right? So now let's do this using the smallest data size possible, either a byte, half word, or a word. Convert the following value into 2's complement representation. So means that you need to have in I think the best way is to use hexadecimal number, right? Okay, so now change this to hexadecimal number. So what is the value? And remember to use the smallest data size possible. Means that you need to convert this to hexadecimal number and check whether it is can fit in word size or half word size or byte size, right? Of course, byte is not possible because this is more than 8-bit already, right? Half word maybe, right? So what is what? So let's look at the first one, A. You can guess this very fast. So I maybe I can show you. Or who want to try A? You need to use your calculator, right? Okay, so you can have the calculator here, your computer calculator. So you change to programmer mode, or if you have um, the uh, the actual calculator, you can use it. Okay, the number is in decimal 18304, right? And this is negative, and we have that. So if we convert to hexa, we have this value, right? We have this value. So what is the smallest size possible? Is it byte? No, not possible byte, right? Because byte you have 8-bit, so you can only store 80. So this is not possible. What about half word? Is it possible? Yes or no first? So siapa betul dapat A. Kemungkinan besar lah. If I say yes, so is it half word? Half word, Okay. Okay, if I say half word, orang lain? Write in the chat je. Tulis kat chat tu. Sama ada half word ataupun word. Byte is not possible already. Word, Okay. Let's see. Fatul. Word. Word means 32-bit. Okay. So ada dua jawapan dah sekarang ni. Ifa half word, and then Fatul would. Okay, lagi. Cepat. Kita nak banyak lagi nak belajar. Half word. Say it. Half word. Okay. Go on. Half word. Saya jawab full. Full. Half word. Oh, tak payahlah. Banyak dah ni. Half word. Half, So, kebanyakan half word. Right. So, the answer is half word. B880 is negative 18304 in hexadecimal, right? So if we this is B880, so B is 1011, 8 is 1000, 1000, and 0000, right? So this is 16 bit, and this is, oops, okay. So this is 16 bit, and this is, yes, this is minus 18 in decimal, minus 18304, right, in 16 bit. Can we store in 32 bit word? Can or not? The answer is can, right? Because bigger, of course, can, right? So if our system is 32 bit, so you need to stand, this is tiny bit, negative. You just extend, you just extend the sign bit to 32 bit, all right? So this is another F, this is 0, this is 8, this is B, so you have another F, right? So if 32 bit here, yes, this is again minus 18304, 32 bit. 24 bit, yes, can. 24, not 24. This is 64. 64 bit, yes, can. But less than 16 bit, cannot. So the minimum, yeah, we need to answer the question. So the question asks you to have the minimum size that can store minus 18304. So it should be 16 bit lah, right? The minimum size that you can store this or half word, right? Get the idea? This is just a revision. You actually have learned this in digital design. What about B, minus 20? Very easy. This one is the easiest lah. Just you can guess only, right? Because remember, the size, yeah, the size of the register, for example, to store an 8-bit number, or the maximum number of 8-bit is in the positive side is positive 127, right? And the smallest number for 8-bit is minus 1 to 8, right? So if you have minus 20, so it is in the range. So you should be able to store in byte, right? Easy. What about C? Very fast. Yeah, come on. Belum dapat A nih. Yes, cannot store in byte. So must be. Kalau tak boleh dalam byte, so must be either half word ataupun word, kan? Yes. So should be half word because you see 144 is not that big. So if it's not uh stored in byte, so should be half word already, right? Or word, tapi half word enough. 144 is very small. What about D? This is not the full answer yet. Yeah? I just asked you whether this is word or half word or byte. So the answer you need to convert into the two's complement representation, which is the hexadecimal number, right? What about D? Is it byte? Yes, byte. All right, because just now, yeah, minus 1 to 8 is still, yeah, the minimum number for byte. So it should be, yeah, it can be stored in a byte size. Now let's look at the last one, minus 1 to 9. Half word already, yes, because it's just uh, smaller than the minimum number of byte already, which is 1 to 8. Yeah, 1 to 9 is minus 1 to 9 is smaller than minus 1 to 8. So it must be half word now. All right. So you can try number 5 also. Here you need to convert first, yeah. So you can do on your own. Number 5 is same thing actually, but the number is a little bit bigger, right? So you can try to do this. Look at number 6. If the hexadecimal value is a two's complement half word value, what would it be in 10 bits? This is interesting. So if this is two's complement half word value, right? So what is the number in base 10 or in decimal? This is interesting. So anyone want to try? Anyone want to try? In decimal, you can use your calculator or you can manually convert to decimal, right? Now let's do that. Anyone want to try? No? It is a negative number, right? If it is in half word value, because look at the sign, right? We have what? We have what is it? FFE3. Okay. We have FFE3. So if we look at the sign, because this is F, this is should be negative number. So yeah, just convert to the decimal. You can use your calculator, right? Uh, yeah, Sayed, minus 29, correct. Okay, so let's use the calculator first, yeah. First, we need to determine whether this is positive or negative, lah, right? So if this is half word value means that it is 16 bit, right? So if it is 16 bit, means that the MSB must be 1, right? Because F. So if MSB is 1, means that this is a negative number. Okay, that is our the first thing that you need to determine. If this is negative, if you want to use calculator, and this will depend on your calculator. So for example, this calculator in uh, the window calculator, the free one calculator, so it is 64 bit. All right, so you can see that the F is extended to bit number 63. All right, the last bit means that in total it is 64 bit. Okay, so if you want to use this, so you need to extend the sign to 64 bit also lah. So what you need to do is you need to write how many F? 1 2 3 4 5 6 7 8 9 10 11 12, and then the last one will be the one that we want to have, which is the FFE3. So FFE3, and then you convert to decimal, and then you will get minus 29. That is how. So it depends on your calculators. If you have the calculator, so for example, in this one, 64 bit like this, so you just need to extend F to 64 bit, and you convert. And if your calculator is 8 bit, for example, not 8 bit, 32 bit, so you just have this, right? And you convert. But if you are lucky, if your calculator is 16 bit, so you can straight away use FF E3 and you get minus 29. Or you can manually calculate using yeah, on paper. So we have FF, we have FFE3, FFE3. So we need to convert this to binary, where we have F, F, E is 1110, 3 is 0010, right? So because this is in binary and this is negative number, right? This is sign bit negative. So we need to complement, yeah, find the complement, two's complement for this. So we have the first complement, we have this, and we have 1 1. 3 is not 1 0, 3 is 1 1. We have 1 1 0 0, right? And then the second complement, we need to add 1. So at the end we have 0 0 0 0 0 0 0 0 0 0 0 1 1 1 0 1. And when you use calculator to convert this to decimal in binary, which is 1, yeah, 1 1 1 1 1 0 1, to decimal, you have 29. So this is 29. And because this is actually a negative number, so it is negative 29, right? That's it. Okay. So now that is the first part. Now let look at the second one. If what if it were a word length value, word, yeah, before this is half word. Now if it is word, what is the value in decimal? If this is a word size, so first you need to determine whether this is positive or negative. So is it positive or negative? If it is word, if word means that the value is ff3 e3, right? If it is a word size, so you should have this 40 before this, then this is word or 32 bit size. So if this is the value, this is positive or negative? Yes, positive. So if it is positive, then you can straight away use your calculator very fast. So what is the value now? So you can use your calculator straight away. So it is FF E3, and you convert to hexadecimal. You convert to decimal, and you have 65507. So this is the value, right? So so that will be chapter 1. So here this exercise is actually just for revision. So hopefully uh, uh, you should be able to do this. You should understand the number system. This before we can learn this microprocessor, because later on when we start to program, write the program for the microprocessor, the number is in this byte, half word, and word, and we will use hexadecimal in the calculation, because the microprocessor using this kind of value, yeah, in the computation, right? So if we want to learn the microprocessor, we need to know how the microprocessor use this number or compute the the number, what happened in the microprocessor, right? So this is very important actually, although it is the basic number